Hello, AP Statistics. This is section 10.2, two sample t-tests for difference in population means. You're going to need a graphing calculator, paper, pencil, note sheets, and your respective tables. Okay, once you have those, bring them back, and we'll be ready to go. Here's what happened in the class today. Students were asked to participate in an IQ test provided by a Mensa publication. Okay, each student was given unlimited time in class to complete the test, though most were able to finish within 30 minutes. During the test, students were asked to use their stopwatch on their phone or to look at the clock to record the amount of time it took for each to complete the exam. Once all students finished the test, the teacher, who was me, read the solutions to the class where students graded their respective work. Okay. Once they tallied the number they got correct, Mensa, the test organization, awarded bonus points for those students who finished their test within 30 minutes. Okay. They also offered a secondary bonus for those who finished within 20 minutes. Students then totaled their complete final score, okay, and then wrote the score on little slips of paper provided by myself, as well as the gender they associate with. Okay. Students did not write their names on their respective papers. Okay. Once I had all the slips of paper, I looked at the data and I recorded the respective scores on the whiteboard. Okay. And here's what I got. First, note that the highest score that anybody could get is a 25. Okay. And that includes the bonuses that were allowed. Okay. You'll notice that I have 15 scores for the males and I have 13 for the females. Okay. And my question is, we will test to see if the mean scores for males are statistically significantly different when compared to females. Okay. So how am I going to do that? Well, I have this understanding first that to find the population average score for an IQ test for all males who are able to take a test is fairly impossible to find, as it is for females. Okay, and while I like to assume that they are probably going to be pretty close to the same, okay, we'll never really know unless we quite possibly take a sample of each and then offer comparisons. Okay, so what I'm going to do is this. We did a sample of males and females from my 4th hour class, okay, and we're going to compare their respective averages, okay. Now, in doing so, we're going to create a population standard for which we think may be true, okay. First, the null is that the average population score for males, IQ score, will be associated with and defined as mu sub n, okay. Mu sub f will be the true population mean IQ score for females. Okay, it is the intention to think that males and females would score the same, okay, or close to the same, with respect to an average IQ score, and that's why we have an equal to sign in the null. However, the alternative is that it may be different. Okay, and remember the alternative always has either a not equal to sign, a less than sign, or a greater than sign. Okay. Now, in order to move through this test, okay, we will have to go through past the first step to the second one and test the conditions. Okay, now we will do conditions for both males and females. Okay, and the first one deals with random. Okay, and we're going to ask ourselves, were the test scores that we got for this IQ exam, were they random? Okay, with respect to each gender. And in all honesty, they were not. Okay, they were independent. Okay, so meaning one score only belonged to one of the two groups. Okay, so they were independent. Okay, however, they weren't random. It was 4th hour. Okay, but for my dynamics of my class, I love 4th hour, and I couldn't really collect data with respect to this IQ test any other way. Any other easy way, okay? And so my female students were also from 4th hour, and they were independent as well, okay? All right, so this technically did not pass, but I'm gonna move through this test anyways, just because in most cases, it'll be documented within a problem that there's either some type of randomization, random assignments, or an SRS of some type. Okay, so look for that when you do the work. Okay, all right, next is 10% rule. Notice that there is no random assignment here, okay, which means that we have to do a 10% rule, okay? And so I only have 15 males, I have 13 females, and if I consider all males who are capable of taking such a test, take a tenth of those, I know that's going to be bigger than 15. And same thing for females. Any female who is capable of, reading a test and taking a test and getting answers, take a tenth of them. I know that will be bigger than 13. So this will be satisfied. This passes the 10% rule for standard deviation. Okay, large counts for normality. Now, remember in our previous section that dealt with proportions, we did n1 times p1, that was bigger than 10, n1 times 1 minus p1, that's greater than 10, and so on with the n2s. And remember that only works with proportions, okay? So if we're dealing with the averages, we need to look at our sample size. And up in the top here where the males are, I'm going to say n was 15 for the males and 13 for the females, and hoping that each of them is at least 30. So I can use the central limit theorem to say that it's approximately normal. However, they're not. Okay, so what did I do? Well, I took my list for the males, okay, that I found it's on the previous slide, the list of males for the data, and I put them in L1. Okay, so I put the list of data in L1 for the males and L2 for the females. Okay, and then once I did that, I did a box plot for each. Okay, and so this one is for the males, of course, since it's under that category, and this one is for the females. Okay, my TI-84 did all the work. You'll notice that there are no dots to the left or the right of your distribution for males. And what does that mean? Okay, well, looks like we have no skewness. Okay, and no outliers. Outliers, excuse that. And what does that mean? Well, it means we have an approximately normal distribution amongst the males. Okay, amongst the males. Same thing for females. Notice that this looks about as symmetric as it could possibly be. And again, there's no outliers. So I'll state that no skewedness, no outliers. Okay, and that means we also have an approximately normal distribution. Okay, and we are able to move on. So step 2 is done, which means we are getting ahead of ourselves, but we're doing now the test statistic, which is step 3. Okay, and in this case, it is represented with a T, okay, not a Z, because we are dealing with averages where our population standard deviation is unknown, okay? And it's set up like this. And I'm going to need my sample averages from L1 and L2, or my males and females, as well as the respective standard deviations for the samples and the sample sizes, okay? So to do so, I'm going to do in my graphing calculator from L1 and L2, from your TI-84, one var stats. Okay, and when I do that, I get those respective windows, okay? And this one here is for males, and this one is for females, okay? And what do I need from this? Well, I need the X bars, of course, and you can just kind of look at this ahead of time. It looks like females are a little bit higher, okay? Higher average than males. The respective standard deviations are your S of X's, okay? And your N's are 15 and 13 respectively for your males and females, okay? You're also gonna need a degrees of freedom, okay? Which is typical for your work with T. And the formula for that did not change. It's N-1 for your degrees of freedom. And the conflict you have is, well, I've got two N's. I've got one that's 15 and one that's 13. How do I do this? What you're gonna do is you're gonna pick the smaller, okay? And so your N equals 13 is the one that we're gonna work with, okay? And that's the one I'll input into our formula. And I'll put all the items from the windows as well as 13 into the formula. and it leaves me with this. Okay, so I'll give you a second to look at that kind of carefully to see how all the inputs from the windows, okay, translated into this equation. And if you were to do the work for it, okay, you would end up with this. Okay, now what does that mean? Well, here's what I'm gonna do. I'm gonna draw the best normal distribution I can. Okay, and down the middle, here's what I'm gonna do. This is the sampling distribution of all mean differences of sample size 15 for males and 13 for females. Okay, there are a lot of groups of 15 I could come up with for males and a lot of different groups of 13 for females. And when you do IQ tests and then averages of those and subtract them, there's going to be moments when their differences are 0. Okay, and so that is the average of the little samples for the males minus the females. Okay, sorry that's sloppy, but that is kind of what we presume to happen, that the males and females averages will be 0. That's what you wrote your null hypothesis as. Okay, now it doesn't quite look like this form, and that's why sometimes people like to write it that way. Okay, even though I think the conclusion reads better the other way, but that's the reason why. Okay, and so typically we hope that it's 0 if the null is true. However, we have an understanding that there are moments when sometimes the X bars for the men or the males are a little stronger than the females, okay, as that would show up on the right side. And sometimes the females do better than the males, okay, and that would be a representation on the left side, okay, as you do that type of subtraction, as you would see in your numerator. So your standard error on the bottom is 0.946. And so I'm going to go to the left here, 0.946. I'm going to put it on top so you can read that. However, if you were to find the full standard deviation, sorry, not the full standard deviation, the full test statistic, you would get negative 2.3948, which means the difference in the two scores between males and females, okay, with respective averages, was 2.39 standard deviations away below the mean, okay, and in favor, I'll just say, of the female average, okay. So what am I going to do? Well, this is the true difference, negative 2.266. And with respect to what I drew here and drawing one standard deviation to the left as being 0.946, I'm going to draw just negative 2.266. Okay, and that 6 may repeat, by the way, and say that is a good looking graph. This is step 4. Okay, and then we'll move on to our p-value. Okay, now how do we find a p-value? Well, typically what we'll do is we'll look at where our test statistic would be on a standardized normal distribution or a t-distribution with a degrees of freedom of 12. But in terms of how I drew this, this is based off our original data. We'll look at our alternative. Okay, and our alternative has a symbol between the two means. And in this case, it's a not equal to. Okay, typically, we sometimes see a less than sign or a greater than sign, and that usually shares which way we will shade, either to the left or the right. If it's less than, we'll shade to the left. Right side will greater than will shade to the right. However, because it's a not equal to, we're going to do two things. Okay, one, we're going to shade to the closest tail. Okay, and find this area. Okay, and then further, step 2, once I find that area, because it is a two-sided test here, I'm going to double my p-value. Okay, now how am I going to do that? I'll do that in my TI-84. Okay, and this is TCDF, if you remember that. Okay, and so my lower boundary for my TCDF command is how far are we going to the negative direction, and you can see this goes infinitely to the left, and so I'm going to just say negative 1,000 there. Okay, and then how far does it go to the right? Well, it stops here at the test statistic, which is negative 2.3948. That is your upper bound. Okay, and then your degrees of freedom, in this case, we said was 12. Okay, again, we chose to lower the two sample sizes. And if you go through that, okay, and you find this area, okay, you will end up with this part that you see just above it, 0.0196. Sorry, I said that backwards, 0.0169. Okay, notice that you have this awesome multiplied by 2. And what does that multiply by 2 mean? Because again, it's two-sided. We have a not equal to sign for our ha. We're going to double our answer. So we have 0.0338 as our respective p-value. Okay. And what do we do with this? Well, we move on to step 5. Okay, and we write a conclusion. Okay, based off this, and alpha was not presented as a significance level was presented in the beginning, so we'll just go with 0.05, which is seems to be pretty standard, and just go with it. And what does that mean? Well, we will reject the null. Okay, based off this alpha. Since our p-value is 0.0338, that is less than my alpha cutoff of 0.05. And then there is evidence to suggest that, and I typically just like to write the ha after that. What is the ha? Well, U of M, the true population mean IQ score for males is not equal to or different than the mean score for females. Okay, and so are we saying that males are weaker or that females are greater? We are not, okay, because when we went into this test, we just wanted to show that they were equal or not equal. And in the end, here's what we found, that there's evidence to say that they were different. Okay. And so there you go. Okay. So those are your 5 steps. Okay. Again, in this case, we didn't have exactly random selection here. This was my period 4. Nevertheless, we were able to do the work for the rest of the data and come up with a conclusion. Okay. Now, with these 5 steps, remember that there are times when you can use your graphing calculator in ways that are different from what you see here to replace work from step 3 and step 4. Okay. So let's take a moment and take a look at that and use that practice. We're going to use our TI-84 to do this same command. And I kept my null and alternative there. And I kept all of our old work. Okay, I didn't rewrite the conditions, of course. But I do have a test statistic. I do have our p-value that we found, degrees of freedom, and our conclusion. Okay. So here's what you can do if you like. You can go to your graphing calculator, go to your TI-84. And we're going to again go to stat, and we're going to go to tests. Okay. And in this case, this is called a 2-sample t-test. That's kind of the short, truncated representation of what you see here as a title, 2-sample t-test for the difference of population means. But it's command 4. Okay, so we'll select that. And luckily for us, all of our work is in L1 and L2. Okay, so there's nothing to really input. If you have different lists there, then of course, identify those. And then further, there's a couple items that we haven't seen before. First one is this pooled, okay? Leave that as a no, okay? Never have yes, okay? We won't use that. And second, this is the first time we've probably had this in a while. We have a not equal to sign, okay? So make sure you identify your not equal to sign in your ha, your alternative. And if you go down and click calculate, okay, it'll give you some important information. First, it'll give you your test statistic, where the t is, negative 2.3833. That's pretty close to what we have here. Okay, why is ours a little bit different? Well, we have a little bit of rounding in the X bar for the males, and the standard deviations are rounded as well, so that could contribute to it. Second, okay, is this guy here. That is your p-value. Now notice your p-value is a little different, 0.0250. okay? That's probably a little bit more accurate than the one that we found here, okay? Note that when you use your TI-84, that it will do the entire calculation for your probability, your p-value for you, okay? Meaning you're not going to have to take this answer that's in your calculator and double it for this respective test, okay? Last thing I want you to notice is this, okay? We use a shortcut to find our degrees of freedom. We just pick 12, okay? Now, is that really the way you're supposed to do it? No, okay? In fact, when the calculator finds the degrees of freedom, okay, it uses this, 25.156. That is my degrees of freedom for this problem, okay? And that looks incredibly different from the 12 that we chose earlier, okay? And so some may ask, is there a better method for choosing a degrees of freedom so that we can have more accurate results, okay? And the answer is yes, you could use the formula. It looks like this, okay? However, okay, because that is so exhausting, okay, we are not going to worry about it. And again, if you want to do the long ways, like we did on the previous slide, you're certainly allowed to use the lower of the two, the smaller of the two sample sizes, okay? However, if you use the graphing calculator, which is my more preferred method, okay, all you would have to do is write TI-84, okay? Again, we're using command toSample t-test. Okay, I'm going to give the t just like I gave before. It's negative 2.383. I'm going to give the p-value, which is 0.0250. I don't have to double it or subtract for 1 or anything like that. And I also want to write the degrees of freedom, okay, and not the one that is the shortcut version. I'll go with the calculator version, 25.156. Okay, so write all three of those. This again is step 3. Okay, this is really also part of step 3, and this is my step 4. Okay, so have those three. Feels like, man, that's a lot of stuff to write down from a calculator output, but I'll tell you what, that's a heck of a lot better than doing what I see over here. Okay, that is a lot of things to, I'll say, potentially mess up on by just hitting the wrong key. Okay, so keep that in mind. And further, look at this degrees of freedom formula. I actually hand typed that in there. That was exhausting, okay? It's almost exhausting just to input the numbers as well and then repeat the commands in your calculator, okay? So this is actually a gift to be able to do that, okay? All right, so I hope you have a good understanding of toSample t-test for difference in population means. Let's go to the interval now, okay? And we're going to do confidence intervals, okay? In this case, 95%. Notice I've still defined the mu sub m and the mu sub f. That's important to note. And we'll start with our 3 steps, the first being the conditions. Okay, now, like previous section, if the conditions were already satisfied in a previous problem, okay, then you don't have to do it again. Okay, so I'm just going to say satisfied in previous work. Okay, now I will tell you, okay, that you're allowed to do that, but make sure you write this, okay? If you don't write it, then it's going to be the understanding that maybe you didn't know that you had to do the conditions, okay? So make sure you write it in. Second thing, okay, here is our formula, and it looks very similar to the test statistics that you found with the t, okay? Notice that this part here was your numerator, okay, the part that you see right here. You have a t, we'll talk about that in a second. And then this is the standard deviation that you had in your numerator, okay, the standard error, excuse me. And so what I'm going to do is I'm going to fill those in similarly to how you did the previous question with your test statistic, okay? So this again looks like the numerator, okay? This part in the back looks like your denominator for your t. And then you'll notice that this t, okay, has a value of 2.179. Okay, and you're looking at that and you're like, where did that come from? Okay, if we go to our table, okay, and this came from, just so you know, www.tdistributiontable.com, They allowed me to post it on here, provided that I gave them credit for it. So there you go. And if I look at 95%, which is down here, and my degrees of freedom, which we said was 12, okay, based off our work. So battleship going over allows me to finish right here. Okay, so degrees of freedom is 12, as we shared before, 95%, 2.179. Okay, so that's how I came up with it. There's not really an easier way that I can think of once you have your table out. Okay, once you do the math, okay, there's your again, the error, the standard error on the bottom, and 2.179 again wasn't calculated in yet. When you do that, you get to this spot, and if you do the entire interval, you end up with this. Okay, now with this, okay, you're going to write a step 3. This is, by the way, step 2. Okay, from your conditions, that was step 1. Sorry, don't mean to backtrack. Okay, this is your step 3, is writing a good sentence. Okay, so if it's a 95% confidence interval that we're seeking, we'll say this: say we're 95% confident the interval from negative 4.32 to negative 1.977 captures the true difference in population mean IQ scores. And notice I showed the direction, men minus women. Okay. A good follow-up question that is sometimes asked is, did one gender do better than the other? Okay. Was there a difference between the scores? Was there a difference between genders for IQ scores? I'm going to say mean IQ scores. Okay, now if there was no difference, okay, if there was no difference between, I'm looking up here in the top left-hand corner, the average for the male and the average for the female, if there's no difference between them, we would assume that that difference is 0. And I'm going to look here, is 0 included in our work? And no, in our confidence interval, 0 is not included. Okay, so there was a statistically significant difference because 0 is not one of the plausible values for the difference in means for the population proportions, population means for males and females. Okay, so again, 0 is not included, so there must be some type of difference, okay, between the average scores. Alrighty. Now, some of you may ask, again, is there a graphing calculator method for this? There definitely is. I saved all the work here for you just so you can see that it's the same. And your first step is to go to TI-84. Okay. And we're going to go to, again, same stuff, stat, and then we're going to go to tests. And instead of going to 4, you're going to 0. Okay. So you're going to go to 0 and write that command. It's to sample t interval. That's, again, a much abbreviated representation compared to what I have on the top. Okay. You could write this big long title if you like. Sounds a little bit better, a little more scholarly, a little more academic, but this would also work as well. Okay. And once you click on that, again, all your data is in L1 and L2. We had a 95% confidence interval. Remember, all of our data is not pooled. Okay. And when you hit calculate, you end up with results that are probably a little bit more exact compared to what we have. Okay. So, but notice that negative 4.32 is very close to negative 4.225, and you have negative 0.1977. That's actually quite a bit different than negative 0.3086. But again, this is a little bit more tighter interval, and it's probably a little more accurate. Okay, I would go with that. When people ask which is the way to go, okay, I don't do this way. Okay, I prefer not to, though it's important to know the components of the formula. Okay, that's often asked on multiple choice. Okay, I go with this one. It's a little bit more exact. I like the degrees of freedom a little bit better than what's provided here, and so yeah, go this way. Okay, it'll look a little better. You'll feel better about having a more complete answer. All right. If you have questions on this work, feel free to ask. Here's your respective assignments. And I hope you have a good rest of your day. Thank you for listening.